Okay then. Well, welcome to Physics 2820, Lecture 13. Today I want to take a little bit of a side trip away from solving analytical problems and focus on some data analysis. So often when you're doing physics, especially experimental physics, you're going to collect some data. And that data is typically going to be recorded in tables, and you're going to have to do some analysis with it. If you remember back to Physics 1050, 1051, we typically would do labs, and in those labs there would be software that would collect data, and then you could click buttons to do things like finding a best fit curve, whether or not that be a straight line fit or a quadratic fit. What I want to do in this lecture is make that work, what that computer is doing, understand that a bit more, so it's not being treated like a black box, just some button you click on an application. But I want to talk about how to actually do data analysis and curve fitting as it applies to data, because it's a computational task and it uses a lot of the same techniques as we've been dealing with when solving equations. Okay, so I've got a lecture in front of me. You should have it as well. We're on lecture 13. Import the stuff as we usually do. And so I want to start with a scenario here. Imagine we're doing some Physics 1050 experiment or some other mechanics experiment, and we generate some data. This data could be in a lab book or collected from a sensor. And what it's really doing is it's storing the position of some ball being tossed up, where its height is being recorded as a function of time. There's lots of ways of writing this data down, but I've written it down in ordered pairs. So basically the time and then the position, the time and then the position, the time and then the position. Perhaps these positions were recorded by some sensor. You can load this into a pandas data frame by having these pairs of numbers and then giving them labels. The first number is the time, the second one is position Y. And nice thing about pandas data frame is it lets us visualize that data as a table very easily. So this is the kind of data one might collect from an experiment. We've already learned that given a data frame of data, to plot it, you can basically just plot one column of data against another column of data. And the way we do that is if the data frame as a whole has the name of df, then df.t is the t column, df.y is the y column, and I can plot that data as a sequence of points on a scatter plot. So imagine this is some information or some data we collected from an experiment. It doesn't have to be a ball being thrown off. It could be any type of experimental observation. What we often want to do is we want to fit a curve to this data in such a way that explains or models the data. So we know that from projectile motion, that a object under a constant force of gravity, constant acceleration, will have a quadratic shape in position versus time. That is, y is proportional to t squared plus t plus a constant. So to achieve that, you could either use a piece of software like you did in Physics 1050, 1051, where there's a graphical user interface and some button marked best fit, or you could use an application like Microsoft Excel for a spreadsheet and do a drop-down button saying I want to do a best fit. What we're going to do is look at how to implement a best fit using code. Within the Python environment, specifically the numerical Python environment, NumPy, there is a command, there is a function called polyfit that does this for us. What this does is it finds the polynomial that best approximates this data up to a certain order. What order means is a line is a first order function, a parabola is a second order function, a cubic polynomial is a third order function. So what you do to use this thing is you've got your data, your time, your x-axis data, your y-axis data, and some degree of the polynomial. And what polyfit does is it figures out what the coefficients would need to be to best approximate this data. So if you can imagine a parabola in the form of something times t squared plus something times t plus something, three constants, what polyfit is doing is giving you back what those three constants happen to be. So the first constant, a, is minus 4.96. The second constant, b, is 3.2. And the third constant is c. Those define a parabola that would trace through these numbers. You might recognize this is kinematics. The formula for position as a function of time is 1/2 gt squared. That's why the number in front of the t squared, minus 4.96, is 1/2 of the common value of the acceleration due to gravity. 1/2 of 9.81, 4.9 something. What you can do is, rather than just printing them out, you can immediately unpack this array of three things, one thing, two things, three things, and store them directly into variables. So rather than having to do this function and then type this out, which is an opportunity to make a mistake, we can just write a comma b comma c equals polyfit of those two things. And by doing that, what it's doing is it's mapping each one of these three numbers to these three variables. To come up with a curve for the polynomial that goes through those points or approximates those points, we could just use a NumPy expression. We could say, okay, I'm going to take the time data, square it, multiply it by this coefficient a, take the time data again, multiply it by b, and then add c to it. So these three things would be yet another series that we could plot. And indeed, if you plot the original data with dots and this best fit curve as a parabola all the way through it, we see that the orange line, which is the best fit curve, is a very good approximation to the data. Now, it's an approximation in the sense that if you actually look at the blue dots, sometimes the blue dots are a little bit below the orange line, sometimes they're a little bit above, but this is the best parabola that minimizes the error as you go all the way through this. But this operation of having to take the parameters and then create an expression for the polynomials is so often used. There's a second function within the NumPy environment called polyval, as in polynomial evaluate. And the idea of polyval is if you just give it all of the coefficients, then it knows how to evaluate these things. Polynomials can be thought of as expressions where there's a first coefficient, a second coefficient, and a third coefficient, where the number of coefficients gives you the order of the polynomial. So if we use polyfit, and rather than splitting everything apart into an A and a B and a C, and we just leave it as some generalized P, then you can pass that P to a function called polyval to evaluate it all in one go. So this is a more commonly way used of doing these evaluations all the way through. Okay, so Sarah's just asked an excellent question. Wait, how does polyfit get those values? I don't think I fully get it. I don't want to leave this as a black box. We definitely will talk about what polyfit is doing under the hood. Right now, it's no different than hitting a button on a graphical interface or using a drop-down menu. I've just given you a black box called polyfit that does this. We'll go through that in this lecture. But the basic functionality is, given some data points, we can draw a polynomial of first order, second order, or third order, or whatever number of order that approximates that data. Let me give you another example. So here is some artificial data. Don't worry too much about how I generated the data. Let's just assume that it came from something and take a look at it. So there is some data. So if I gave you that data and I said, investigate that data, plot that data, you may recognize that this data follows approximately a straight line. That is 0.5, 1, 1.5. Can you see how the numbers are generally increasing with time all the way through? So an appropriate best fit curve might be a 1-degree polynomial, otherwise known as a straight line. So what we can do is we can fit this data with a one-dimensional polynomial. We're going to get some coefficients, and then evaluate those coefficients as a 1-degree polynomial, otherwise known as a straight line. Graphically, what that means is our original data, 1, 2, 3, 4, 5, 6, 7, 8, 9 points. This could be constructed from some experiment or what have you. The orange line is the best fit curve, as in of all the lines you could possibly draw, this is the line that approximates the data the best. The parameters for this, the coefficients, are 1.59 and 3.26. What does that mean? What it means is this is the first coefficient in a polynomial that would be a constant times x, and this would be the second coefficient, the constant. A line is typically represented as an equation, something like y equals m times x plus b. So this is the m, this is the slope of the line, and this is the y-intercept, the b. Now, these numbers are a good approximation of what's going on. They go right through it, but I think it's time to answer Sarah's question, which is, okay, you've showed us this black box, it comes up with numbers. What is actually going on? So to be able to do that, what I'm going to do is I'm going to stop sharing this screen for a second. I'm going to stop sharing myself for a second. And we're going to do some pen and paper work, because I think it's best to explore this. I would normally do this on a blackboard, but we'll do what we can. What we'll do is zoom in. Okay. Oh. Hey, how about that? Okay. Hopefully that's readable. Here's what I want to go over. This idea of what does a best fit curve mean, and how would we go about implementing a function like polyfit? So let's first talk about this example where we had some x and y data. And the idea is, collected from something, we may have had a bunch of points. And what we're trying to do is we're trying to figure out the line that goes through those points the best. Well, to do this operation, you have to understand that what you've got is a sequence of data points, right? This first point is the point x1, y1. This second point is the point x2, y2. This is x3, y3. In general, we could talk about the points xi, yi for each and every one of these points. And there might be a total number of points, so we might say something like let n be the total number of points we're dealing with. Okay, we want to figure out what the slope and the intercept is that best approximate this data. So the goal here of what we're trying to do, what we mean by a best fit curve, is find a line, okay, and I'm doing the one-dimensional case here, the first order one, and the line would be written as find some line that is the closest fit to the data. When we talk about lines, right, the two things we're really looking for are its slope and its intercept. So I could draw lots of lines. I could draw this line. I could draw a line that's a little bit more of a slope, a little bit less of a slope, shift it up a little bit, shift it down a bit. By varying m and b, those are all the possible lines I can draw. When we talk about a best fit or a regression line, we're choosing the m and the b in a way that minimizes some kind of error. In this discipline, which is part of statistics about regression analysis, the error that we want to reduce is the distance from each one of these points to this line. So if you think about this distance right here, that is the distance from a point on the line up to where the point actually is, that interval is called a residual. You can calculate a residual for every one of these things. Residuals can be positive, residuals can be negative. They're the difference between the actual data and the value of the function evaluated with a special choice of m and b to get it all the way through. The goal in finding the correct m and the b is to figure out a way in which all of these residuals are as small as possible. Before I do it for this problem, let me do it for the zero-order polynomial, because I think that's easier to understand. So again, imagine that I've got some data. Okay, so those are 4 points in XY space. And suppose what I'm looking for is the best zero-order polynomial that approximates that data. What do I mean by zero-order polynomial? Well, I mean a function of the form y equals k, where k is a constant. That's the easiest kind of polynomial. It doesn't depend upon x at all. The question is, what line should I draw so that the errors, technically called the residuals, are as small as possible? So imagine I have this kind of data, okay? And specifically, each one of these points is some point xi, yi. This distance from the line to here is called a residual. And this function is what I'm trying to search for. What that means is the residuals are always equal to whatever the point of whatever the function actually is. I'll do it this way. Whatever yi is minus k. Yk, because that's the function. Now the idea here is k I don't know. I'm going to try to solve for k. I'm trying to figure out what k should be. I want to figure out Ri in such a way that all of these errors are as small as possible. If I want them all to be as small as possible, one thing I could do is I could sum them up. Now, there's a bit of a problem with this. You could imagine a scenario where half of the points are above the line and half the points are below the line. So the error, when you add up all of those, they start to cancel together. So you come up with a net total residual that would actually be 0, even though there's clearly some error. So one of the things we do is, rather than talking about adding up all the residuals, what we do is we add up the squares of all the residuals. This is the sum of squares of the residuals. The error or the residual in every one of these values, add them all up, square them all, add them all together, and that gives you some measure about how good a particular line would be. If the line's in the middle, the sum of all those errors will be relatively small. If that line was much higher or much lower, the total net error would be less. This thing that's the sum of squares is typically given a symbol like capital S. So this is the sum of squares. What I want to do, in a best fit sense, is I want to find the value k so that this thing is as small as possible. So what you have to imagine is there are lots of choices of k. For every one of those choices of k, you would get a different sum of squares. For some values of k, the sum would be quite large. But if I just chose the right value of k, there might be some special point where there still might be some error, but the sum of squares would be as small as it ever could get. This is an optimization problem. So if you've done this in calculus, if I have a function, s of k, and I want to figure out where its minimum is, what value of k makes it minimum, one of the things I can do is look at the derivatives. I know from calculus that the derivatives of these functions are found when there are critical points. That is, points when ds dk is equal to 0. This is going to give you all of your critical points. And this can be used to find your minimum. Well, how are we going to find this for this expression? What we're doing is we're taking this equation right here, and we're taking the derivative with respect to k. In this evaluation, yi is just a number. It's known. It's the data points we're given. So if I want to figure out what ds dk is, what I'm going to do is I'm going to take the derivative of this expression. Now, these are just sums. Because they're just sums, the sum of a bunch of things is just the derivative. The derivative of a sum is the sum of the derivatives. So that means we can just take the derivative of each term independently all the way through. Well, the derivative of yi minus k squared would be 2 times yi minus k times the derivative of the thing on the inside with respect to k. So that's how you do that. Even though it's under a sum, the derivative of a sum is the sum of the derivatives. We want to solve this for when this is equal to 0. Well, if we want to have all these things equal to 0, that's exactly the same thing as saying the sum of yi minus k is equal to 0. Because the only way for this thing to be equal to 0 is if those things all add up to 0. If you split this apart, k is just a constant. This is just the same thing as saying y of k minus k times the sum of 1 is equal to 0. There's a summation in here. So what you're doing is you're adding 1k, a second k, a third k, a fourth k. That is to say, k is just equal to the sum of all yi's divided by the sum from I equals 1 to n. Well, that's just n. And you might recognize what that is. The sum of a bunch of data points divided by how many data points there are. That's just the average. So what this analysis is showing is the function that best approximates constant data would just be the average of all the points. So if you had to write a polyfit function order 0, the way you could implement it is just take all the points in y, add them up, divide by n, and that's going to be your coefficient. Okay, but that's for a 0 order degree. Okay, otherwise known as a constant function. What we want to do is we want to do a line. We want to do something a little more complicated. Okay, here we go. What we want to do is we want to figure out the sum where the residuals, or the sum of the squares, is as small as possible. To do that, we think about what the residuals would actually be. They would be every point yi take away mxi plus b squared. So this part right here, this expression is the line we're trying to fit to. It's every point along here where m and b are the parameters we're trying to solve. And yi is the value of the function all the way through. As before, whether it's a one-dimensional or a two-dimensional function, to figure out its minimum, one of the ways of figuring out its minimum is to figure out where you've got critical points. To figure out the points where ds dm is equal to 0, and figure out the points where ds db is equal to 0. Points where those two things are both critical points is where the minimum of this function is going to be for any possible m and b. Okay, so how do we proceed? Well, what I have to do is I have to take this expression and take the derivative of it. Again, the sum The derivative of a sum is the sum of the derivatives. So that's just going to be equal to 2 times yi minus mxi plus b, close the bracket, times the derivative of the inside. And what's tricky about this is the derivative here is with respect to m. It's not with respect to x. It's with respect to m. So if you look at this expression, what's the derivative of this whole thing with respect to m minus xi? We can do the same thing for the second one. I want to add these all up. I'm still going to get a 2 times yi minus mxi plus b. Now the derivative of the thing on the inside with respect to b. Well, as far as b is concerned, constant, 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 you're left with a minus 1. What these two equations are going to give you is equations that need to be solved for m and b. As we saw in the previous example, 2 in the minus sign, if this whole thing is equal to 0, that means this expression times xi has to be equal to 0. And this times, well, 1 cancels out, has to be equal to 0 as well. So one way we can write this down is we could say the sum of all the yi's multiplied by the xi's, this multiplied by this, minus m times the sum of all the xi's multiplied by the xi's, because you're multiplying this times this, minus b times the sum of all the xi's is equal to 0. So what we're doing is we're just imagining this is a long sum and expanding all those terms out. Do it again for this equation. The 2's and the minus 1's don't come into play. What you're left with is the sum of all the yi's. This guy down here would be minus m times the sum of all the xi's. And this guy here would be minus mb times the sum of all the 1's, all the way through. And again, when you add up all the 1's, that is I equals 1 to n, this thing here is just n, the number of n's all the way through. So these are isolated bits. And what it tells us right away is the b will be equal to, when I solve it, that is put this on the other side and isolate it, will be equal to 1 over n times the sum of all the yi's minus m times the sum of all the xi's over m, not m, over n. You might recognize these things. This is just saying that the interface is the average value of y prime minus whatever the slope is times the average value of x. So if you want to write your own polyfit, you can figure out the coefficient related to the intercept by just taking the average of the all y's minus the slope times the average of all the x's. This is basically just saying where the center of this happens to be. That's what we're really figuring out. And then we slide it down to the intercept. That's all that the result gives. The more interesting one is how you go about solving this equation right here. All that is solving that top equation. Solving it now is doing a substitution. Substitute this inside here. So what you're going to get is the sum of yi xi minus m sum of xi xi. The b would just be equal to minus y bar minus y x bar. And then we're going to have a sum of xi is equal to 0. Okay, you can take this and you can solve it for the m's. Let's group all the terms with m's together on their own. So what I'll be left with is I'll be left with an m of sum xi, that's the sum of squares. I'll be left with minus a x prime sum of xi. Put that on one side and leave on the other side everything that's left over, sum of xi, yi, minus y prime, sum of ix. Now, these sum of xi's, you might recognize those as being themselves just averages. So typically what we do is we rewrite this as the sum of squares. This thing is rewritten as n times that. What you're doing is sort of like dividing by n and multiplying by n, turn that into an average. And this guy becomes n times y bar x bar. And so the big takeaway is sum of yi xi minus n times y bar x bar, all divided by the sum of xi minus n. Okay, all of that is to say that if I gave you some data like this, and I wanted you to calculate what the coefficients were, the absolute best value of m and b, what you would do is you would take all those coefficients and you would write a piece of code, and you could do this, that looped through and added up the products of all the components together, calculate the average of y, the average of x, divide that difference by the sum of all the squares of the x's, minus by n times the square. You can actually rewrite this if you take statistics as the covariance of x and y divided by the variance in x. That's what that means mathematically. But this plus this give you the coefficients all the way through. What this is meaning is this is what is being implemented by a function like that. It's giving you back the m and the b. We don't want to have to do this all the time, so we implement this as a function. Now, PolyFit does a few more nice things. It does it for not only, no, whoa, I lie, it's a 1. It can do it for first order, 0th order, second order, third order, fourth order. There are ways of doing this derivation to basically get this into a large matrix that needs to be inverted. See a course on linear regression for the details. But what PolyFit is doing is it's figuring out the coefficients that minimize the squares of all the residuals. This is often called a least squares best fit, in the sense that the sum of the squares of all the residuals are minimized when you choose the right coefficients. So, to answer the question of what is NP PolyFit doing, what it's doing is it's taking some data and applying some statistics to try and figure out what the best value of m and the best value of b that minimizes the least squared error all the way through. So that's one of those calculations that you do once in your life. I realize, thank goodness that I have a computer and I don't have to do this with pen and paper. These techniques were developed several hundred years ago when you had to do this all by pen and paper. Or even with a calculator, it would be painful. This is why we reduce these things down to buttons, but you should know where these things come from. There are other algorithms that will give you the same information, but that's what a least squares fit is. Okay, before I walk away from that mathematics, any questions about how least squares is set up or what we're really solving for when we say least squares or a best fit? Okay. Let's switch back to the lecture proper. Okay then, so let's review. Given some data and a bunch of dots, what PolyFit is doing is figuring out the polynomial that minimizes the error in a least squares sense. That is, if you draw vertical lines, measuring that distance, square those distances and add them all up, this is going to be the slope, and this is going to be the intercept of that line. That's a best fit line. Okay, best fit lines can be done not only in this way of setting them up as a sequence of equations and inverting a matrix, but they also can be done with nonlinear methods. Linear here does not mean straight line. You can do a linear fit of a quadratic or a cubic or a quintic. There are other ways of solving these things. Typically under the hood, polyfit solves a linear system of equations. Okay? So this expression is giving us the coefficients or the answer to a system of algebraic questions. But we're also able to fit data to curves that are not polynomials. Within the SciPy package, there is a bunch of functionality used in scientific purposes. So NumPy, SciPy is a bunch of functions that implement things used in science. Specifically, there's an optimize package that optimizes or minimizes the error. I can bring that in by saying from SciPy import optimize. And inside optimize, there's a function called curve fit that will take any function, not just a polynomial, but any function, and try to minimize, in a least squares sense, what the error would happen to be. The way you use this function is you first have to define the function you want to fit as a Python function. So let's do it for a straight line. It should give us exactly the same answer, but it'll illustrate how to use the function. I'm going to define my own brand new Python function. It's a function that takes an argument x. That's the x in y equals mx plus b. And then it takes two other arguments that are the parameters. And what it does is it returns the combination m times x plus b. We could stick in any function we like in here. I'm just using the straight line function because we know what the right answer should be. The way you use it, this function curve fit, is you call it, you give it your model function, and then the data. And what it's going to give you back is two things. The two things are the parameters it's looking for and a covariance matrix. Okay. Those first thing is just the numbers, the coefficients. That is the value of m and the value of b. And you should notice that the 1.59 and the 3.26 are exactly the same. But what curve fit is also giving you is a bit more information. It's giving you back this thing called a covariance matrix, another block of information. This block of information is related to the covariance of how these two parameters relate to each other. The covariance of some quantity you're solving for with respect to itself is called a variance. And you might be familiar with something from first year called a standard deviation. And when and if you take a course in statistics, you'll learn that a standard deviation is the square root of the variance of something. See a course in statistics for what this all means. But what it's telling us is from a covariance matrix, if I just take the diagonals, this bit and this bit, and then take the square root of it, those are giving me the error in each one of these two numbers in the form of its one standard deviation away. All these statistical techniques are estimating what these two parameters are. They're not exactly right. They're just based on the data you've been given. This is my best guess on what the parameters, one of the slope and the intercept, might be. This is telling you what the error is in this guess. In the sense that, and I'll give you some code just to write that out so you can see it, the slope is 1.59 plus or minus one standard deviation of 0.25. B is 3.26 plus or minus in a one standard deviation sense of 0.67. That's what this more advanced statistical technique is giving you, is it's giving some information on the error bounds. You can do this also with pen and paper, but this function gives you that additional information. The linear fit stays exactly the same. So if I just take those parameters the p-ops, the parameters that come out here, and I pass them into this linear function, I will get the exact same result that I had before all the way through. To be clear, this was a fake example. I artificially created the data. So let's now go back to how I created the data. And you can see that what I did is I created a function that I knew had a slope of 2 and an intercept of 3. I added some noise to it to make it look more random, but this is the true answer of what the slope is and what the intercept is. The idea of these best fits is we don't know what these parameters are. These are what we're trying to determine based on seeing the blue dots that we see right here. And we can see that this method is coming up with an estimate for what those things would be. The true value for what the slope of the data is 2. My best estimate for it is 1.59. The true value for the intercept is 3. My best guess for it is 3.26. Whether or not that's a good estimate or a bad estimate is why you need the error calculation, the standard deviation. So what we're really reporting is the slope is 1.59 in a confidence interval based on the standard deviation of plus or minus a quarter. And within that interval, you're going to hit 2. Within this interval of plus or minus 0.67, you're going to hit 3. Again, 1 standard deviation, 2 standard deviations. So you may have to multiply this by 2 and depend on the distribution. See a course in statistics. Cassandra, is the pop matrix similar to the arrows given when you use lin-s in Excel? Probably. And it's entirely possible that the code behind the scenes is actually identical, whether or not you call it from Excel or you call it from Python. Some of these equations, these calculations were written up in the late 60s and the 70s, and they've just been iterated through since then. So it may not be just similar, it may be exactly the same. Okay, let's do something a little more interesting. Let's not just do slopes of straight lines. Let's look at this data set. So again, pretend you don't know how it gets created, but here's the data. So if I give you some data like this, imagine you're doing some experiment, and this is what you get out. This is your variable. This is a knob you're turning in the experiment. This is the output of the experiment. There's your curve. And we're trying to figure out the line that goes through this data. Well, it doesn't matter if we try a linear, a quadratic, or a cubic fit. None of them are especially good. So if I take that data, and if n is equal to 1 or 2 or 3, and for any one of those orders, I figure out the parameters for an order 1 function, an order 2 function, order 3 function. I evaluate that polynomial and then I plot it. I would get the orange line for the linear function. The green line gives me the quadratic approximation. The red line gives me the best cubic. And you can see that as you increase the order, it does get better, but none of them are especially good. And that's because this data is not really a polynomial at all. This data isn't a polynomial. There is no polynomial, that is something with x squared, x cubed, x to the 4th, that will ever go through all these data. What you want to do is you want to model this data with a function which has the right mathematical form. And you get this from the physics of the problem. So if you're doing an experiment, you need to bring to it some model, some physics of how you expect the data to behave, and then you can fit parameters around that. Well, this particular function, called a Gaussian, a bell curve, if you will. It's a function that can be described with the following parameters: an amplitude, a mean, and a standard deviation. And in a book, you could look up what a Gaussian is. This is a function that basically looks like this. It's this bell sort of shape. If I go out to very long distances away, it goes perfectly flat for large values of x. The first parameter is controlling how tall it is. So you see this is a 1. If I make this a 5, the function gets a lot taller. This second value is figuring out where the center of it is. You see there's a 0 right there. If I move that to becoming a 4, the center now is at 4. If I make the center equal to -2, it's over at -2. And this last parameter is the standard deviation of this Gaussian. It's really how wide it is. So if we double the standard deviation, it makes it wider. If we make the standard deviation much smaller, it makes the peak much sharper. So this is a general family of equations called Gaussians that have this sort of bell shape. This data, it has a Gaussian profile with some noise. The task here, and this is a common task in experimental science, is to figure out what the best amplitude, mean, and standard deviation is that approximates that data. So that's the goal, is try and figure out or fit a Gaussian that approximates this data. Well, if I just draw any old Gaussian, it won't necessarily match up. I could play a game, try to adjust the amplitude and to make it fit by eye. But I also could use this curve fit function to figure out those parameters for me directly. What curve fit does is it takes any function that you define and tries to map it to this data. So it minimizes the error in a least square sense and returns back the coefficients of that function that work. So if I do that, I get the following coefficients. An amplitude of something just a little bit shy of 3. That makes sense. The mean is at 1. That makes sense. And a standard deviation of 1.5. Again, if we use this function or any other function that gives you a covariance matrix, then you can also calculate what the errors are. So we can say that within one standard deviation, these are the estimates of those parameters. And again, I can now take that, pass that into the original function, and I get a fit of this kind of curve. So this comes up in experiments all the time. When and if you take physics 3900, so experimental physics in third year, you use this kind of thing to figure out what the shape is of this function, even though there's noise. Curve fit is a function that needs to be used carefully. Sometimes when you're doing a fit, it will find a combination of parameters which isn't the one you're looking for. And often what you need to do is you need to investigate something called P0, which is, and if you look this up in the documentation, P0 is an initial guess for the parameters, okay? If you don't give an initial guess, it's just choosing, it's guessing a 1 for all the parameters. But sometimes when you're using curve fit, it's very helpful to give it an initial guess, something that's close. So for our data, we might say, okay, the amplitude's 3, the mean is 1, and I don't know what the standard deviation is, so I'll just call that 1. That would be a good guess, and you need it to be able to solve them in practice. Oh, there's an audio issue. Okay. I'll get Kyle to turn on his mic so he can explain to me what's going on. No, there's been no change in the microphone at all. So those of you who can hear me through Zoom, is that working okay or not okay? Yeah, so something in the classroom speakers. Isn't it great we've got Kyle? I will happily pause for a moment until Kyle's got this all figured out. Okay, I'm glad it's good now. So where did we get to? The point being, we're talking about how to fit nonlinear data. What these examples are doing is showing you how to make this curve, And what I was just talking about at the end is this function sometimes, depending on the data and the function, doesn't work as intended. And one of the things you should look at almost right away is whether or not you need to provide an initial guess to the data. Take a look at the documentation of curve fit when you want to do that. Now, this idea of curve fitting is similar to, but really different from another word which you'll sometimes hear, which is called interpolation. Interpolation is the idea of taking some dots and drawing a line through them. We're not going to do much with interpolation, but I want you to understand the difference between the two words. A best fit is something that minimizes some residual error. An interpolation is a function which goes through the points exactly. I'll just give you an example. Here is some data, and how it works isn't important. I want to focus on the plot. Here is some data. The blue dots are the data. An interpolation, a linear interpolation, would be take each points pair by pair and draw a line that goes through them. This is the default in a lot of graphing programs. They tend to just connect the dots all the way through. When we're talking about data with errors, it's not helpful to always connect the dots. Often what we do is we want to plot the data without the lines being there at all, because it suggests there's structure to the data that's really not there. A best fit curve would be the best single straight line that approximates all of the data. A cubic interpolation is the best cubic function that goes through every 3 points in a sequence. If I give you 1 point, 2 points, or 4 points in a sequence, if I give you 4 points, 3, 4, this cubic is uniquely being set by those 4 points. If I consider this point, this point, this point, and this point, this cubic is uniquely set. And what a cubic interpolation is doing is finding the set of cubic functions that approximate this data, such that not only do the data connect at every point, but their slopes and their curvatures are also the same. But that's it. This is what's called a cubic interpolation. That's different from a cubic fit. A cubic fit is the best cubic function that approximates the data overall. So sometimes you have these options in graphing programs that let you do a cubic interpolation or a linear interpolation. That might be what you want, but probably not. This is not really an error, zero error kind of thing. There's error, as there is in any real experiment. The other comment that I'll make up is when you're dealing with approximations, there's a way of overfitting the data. So if this is a straight line and this is a cubic, you could imagine what would happen if I kicked it up a notch. So let me just do that. Let me just take this code. It's exactly the same code. Okay. We'll just do one plot of it. No, I don't want to change everything. Okay, so there's the original code. I'm just going to focus on this one. Let's get rid of these interpolations all the way through. So I'm going to delete everything having to do with an interpolation. So it's really clear that we're talking about best fits all the way through. Rather than a linear interpolation, I want to talk about overfitting. The idea of an overfitting is when you do a polynomial. So there is the best quadratic that fits the data. There's the best cubic that fits the data. There's the best quartic that fits the data. There's the best quintic that fits the data. And if you go with a polynomial, which is of high enough order, you always can fit the data. There's only 1, 2, 3, 4, 5, 6 points in here. A polynomial of order 7 goes through all those points. If I have data and I overfit it, it will find a polynomial that will go through it, but you've lost all useful meaning. When you're doing best fits, your order should always be considerably lower than the number of points all the way through. Okay, so overfitting, the danger of going up too high in polynomials. Typically, you want to choose the fit based on some reason from physics. Question from Cassandra. What kind of situation would you need to fit multiple cubics to a set of data points using interpolation? Smoothing. Often you've got some data that you want to make it look a little bit prettier and not as jagged. Cubic interpolation is a good way of making that data look better. It's not so clear when you're talking about one-dimensional data, but if you've got data that's projected in 2D, like a graphic, an image, rather than having the data change quickly from point to point, cubic interpolation is a way of smoothing that data so it just looks better. It's good for the eye to see the overall structure of patterns. So cubic interpolation is used everywhere. Let's just see what. Oh, I don't want a video. I want some pictures. Cubic splines. Just trying to find a good example here. Yeah, imagine you were building a video game and you wanted to render some thing in three-dimensional space. You could draw everything in straight line segments, but it may look prettier if you do it in these nice flowing arcs. This is a cubic interpolation. Alternatively, imagine this is your original data. You can use different types of curves. This is a bilinear. This is basically a linear interpolation. This is a cubic spline. Can you see that when you do that interpolation, this data, which is very difficult to see the pattern, it actually looks like there is some structure over here. There's sort of a red region here and a blue region right here, but you can't see that in this low resolution data. The cubic spline filters out the noise and lets you see it. So lots of ways of filtering data, making it smoother. Here's another one. This is a common example of filtering. This might be the raw data. What we've done is we've used some interpolation to make it look smoother so our eyes see it better. And there's several of those techniques out there. So they're used all the time, just that's maybe not what you want to use when you're talking about a best fit curve. Okay, let me finish off this lecture with an application of fitting to some actual physical data and see if we can use these tools to derive some parameters. In your files that you have, you should now have a new subdirectory called data. If you were to look at that subdirectory, there will be a CSV file. That stands for comma separated values. You might be familiar with these things from spreadsheets. Double-clicking on the thing will give you in Jupyter a representation of this as two columns. What we can do with pandas is we can read any CSV data in directly, and it will produce the data frame that represents this data. This is a really nice way of saving data to the disk as a common separated value and then getting it into Python. Almost all software that works with data is able to read and write a comma separated value format. So this is a really good way of dumping data from, say, an Excel spreadsheet into a file that you can bring into Python. What it's doing is it's automatically looking at the file, recognizing there's a header, and pulling out the head, the first bit of it, all the way through. We can plot that data. This is just a bunch of dots closely spaced. This represents an object that's falling. It's falling, which means it's going to accelerate at the beginning, but you can see that it reaches terminal velocity. I believe that this data, I don't know where this data is taken from. It could be synthetic. It's just a falling object under, with air drag all the way through, so it reaches a terminal velocity. Once we've got that data, we can manipulate in different ways. We could take that position time data and we may want to figure out the velocity of it. Well, we know that to figure out the velocity, we've got some techniques. One technique we can use is a center difference scheme. So every one of the dots that's in here that represents the data, these pairs of numbers, I could calculate a center difference scheme by first creating a variable within the data frame called V, filling it as blanks to begin with, and then using a center difference scheme to figure out the velocity all the way through. So there's the velocity, and what you can see is the velocity starts off at 0, quickly gets larger, this is it's accelerating under gravity, and approaches asymptotically some value. What it's approaching is the terminal velocity. If I wanted to calculate the acceleration of this object, I could either take the derivative of this again, that probably would introduce more error, or I could go and use a center scheme directly for the second order, all the way through, as we've talked about before. So this is taking the original data, position as a function of time, and figuring out what its second derivative is all the way through. How we would code that up is we start by creating an empty column in the data frame, loop through all the interior points, and evaluate this formula. Now, as I've talked about in previous lectures, taking derivatives is inherently a noisy operation. The subtle error that's in the data, even though you don't see it in this original thing, you start taking pairwise derivatives of things, you actually find out that there's quite a lot of noise in the signal. Now, you can still see a pattern. Over time, the acceleration starts pretty negative and approaches 0. It's starting near negative 9.8. It's approaching 0 as you get to terminal velocity when there's an equilibrium between the downward force of gravity and the upward force of friction. Let's assume we're dealing with a linear drag law, so something where it's falling proportional to the velocity. One of the things we might want to do in the analysis of our data is to figure out what that drag coefficient happens to be. We always start with a physical model. We need to have some way of interpreting the picture we're looking at. Newton's second law, F equals ma. In this case, the m and the a, the forces, are equal to a drag force pushing up and a force of gravity pushing down. If my goal is to determine what the coefficient of friction is, then when I look at it this way, you should see, oh, that's not working out so well. I'll use, when you look at this thing, you should be able to see this is the equation of a straight line, in the sense that this first bit would be the y. It's the slope times something. Okay. Oh, m's a poor choice of symbols. I'm using m and g in two different ways. Oh, that's bad. Okay, so now b doesn't represent the intercept and m doesn't represent the slope. It represents the mass and the coefficient of friction. Oh, that's annoying. Doesn't matter. The point is, can you see this as being the equation of a line? Something is equal to a slope times a variable plus a constant. If I could figure out the slope of this line, that would tell me what the coefficient of the drag is. When I do that, what I need to do is I need to make a plot of this combination m times a and plot it against minus v. When I make that plot, the slope of that data will have a slope of b, that is the drag force. We will need to know some parameters. We're going to need to know what the mass of the object is. So let's go to a scale and say we measure our object. The object in this case would be 0.2 kilograms. And we can use the acceleration of gravity that we know. And we can make a plot. Okay, so this is a plot of the data where what I am plotting is minus v on the horizontal axis and m times a on the vertical axis. The reason I'm plotting those two things together is because my physics is saying they should give me a straight line. If they don't give you a straight line, it means you have a poor physical model. You haven't understood the physics of what you're doing before. but it does appear to be mostly a straight line, and I want to figure out its slope. How would I figure out its slope? Well, a quick and easy tool is just use polyfit. Given this data, where minus v is on the horizontal and m times a is on the vertical, tell me what the coefficients are. Uh-oh, we got a problem. It is giving us something about on entry DLALC parameter 4 as a legal value. Now, this is one that might start you for a moment, be like, what do I do? The issue in this particular case is there are some nans in the table. If I go back to that data, the first two and the last two values of velocity and acceleration are not a numbers. The reason they're not a numbers is when we did the center difference formulas, we couldn't compute the velocity or the acceleration at the first time or the last time because they depended upon the position before and afterwards. We just left them out. One solution is to take any of the rows in a data frame that have not a numbers and just drop them. So this is pretty common in pandas. There is a function called drop not a. Basically drop anything that's not a number. It removes all of the rows in a pandas data frame that contain not a numbers. And you can see that now the head, or the first few rows, does not contain that data at all. Basically, we erased this and pretend it didn't exist. Now that all of the data are true numbers, we can solve those equations, and we get these two numbers. Now, if you didn't want to drop your data, you could always have used a forward difference and a backward difference to estimate the velocity at the two endpoints. So these are the parameters of this data, the slope of this thing right here. Let's take a look at what that would look like in terms of a graph. So this is the best fit, the line that minimizes all of the regressions all the way through. If you think about the parameters involved, and this is just a tight way of representing those two parameters. I wanted to cut off some of the numbers here, so I'm just using some formatting wizardry. It's just a format string. The first number here is the slope of the line. It's the value b. It has units of kilograms per second squared. Okay? This is the drag coefficient. The second thing in this model, the intercept, and we know this because of a physical model, because we wrote down the model is MA, vertical, equals B times minus V, horizontal, minus mg. The minus mg is going to be the mass times gravity. That third parameter, which works out to being minus 1.962, okay? Oh, there it is, 1.962. This should be the same as minus mg. Well, let's actually calculate m times g, and you get the same number. So this tells us I've got a good physical model. That's one way of solving these problems. And it's the kind of way that I think we did at least for a few labs in Physics 1050, where you project the data as a straight line so that you can do a straight line fit. But what we've covered in today's lecture is the ability to do nonlinear least squares. That is, fit curves that are not straight. We could fit this curve directly. All we need is a model to show how height is going to depend upon time. Well, what that means is I need to take that original equation, the original bit of physics of the problem, and I need to solve this. I need to solve it for y. Now, what do I mean by that? What I mean is, this is the differential equation I want to solve. The acceleration times the mass, ma, second derivative position is acceleration, is equal to minus a drag coefficient times the velocity, first derivative, times m times g. This is something which can be solved analytically. And if you're doing or have done a course in ordinary differential equations, you may know how to do this. But there are tools and packages out there that can solve these analytical expressions symbolically for you. One of them is the SymPy function, and we'll talk about this later on in the course, but it's a way of manipulating these symbols purely the way you would do it with pen and paper to come up with the solution to these kind of things. You can do it only when an answer exists, but SymPy is able to symbolically manipulate this and figure out that the general solution to this differential equation is given by here. The m and the g and the b are coefficients or parameters, and C1 and C2 are related to the initial conditions, the initial position and the initial velocity. Well, what we can do is we can model that function, C1 plus C2 times the exponent of b minus b divided by m times t plus this coefficient, use curve fit to figure out what those parameters would be, and get back directly these parameters. The first one is the value of b. Well, we recognize that as being the same as what we had before. The second one is, based on the data, the value of g. And these last two are these coefficients. Now, I don't know about you, but it's not obvious to me what these two coefficients mean physically. It would be better if we wrote the solution to this problem in such a way that we knew what C1 and C2 meant. They're related to the initial velocity and the initial position. So what's a bit better is if we were to solve this equation, not in terms of some arbitrary constant C1 and C2, but with respect to the following initial conditions. So what that means is, and this is more SymPy stuff, basically what I'm saying is y of 0 is equal to y little 0, and the derivative is equal to v little 0. This is SymPy notation to be able to encode this up, and then I can use that same solver to tell me the answer. To be clear, there's nothing in this lecture that I've explained on how SymPy works. We will talk about SymPy at a later time. Take it at this point just to be a tool. Someone gives you an analytical expression, or you learned how to do it in math class. You know how to go from this equation at the top with these initial conditions, and you get some response. This is the mathematical model. This is what we derive from the physics. It's got a bunch of parameters. It's got an initial height, an initial velocity, a b, and gravity. So what we do is we write all those parameters in. This now becomes the model that we're trying to fit, and when we do a curve fit. And that curve fit, what it will do is let us solve for the drag, gravity, the initial position, and the initial velocity. And now if you go back and you look at this problem, for this particular problem, y was exactly 100 and v was exactly 0 all the way through. The point being, with these non-linear curve fitting functions, you can fit much more complicated models than just lines and polynomials, but it does require a little bit of thinking how to use it. In terms of comparing it to the original data, there is the original data in dots with my first way of doing it plotted on top, or the second way of doing it plotted on top. There's so much data here that you can't actually see it. So what I'm going to do is make the exact same plot, but what I'm going to do is use xlim and ylim to effectively zoom in on a box that looks like this. X goes from 7 to 8, and y goes from, oh, a box that looks like this, sorry. I want to clear my drawings. Box that looks like this. If I do that zooming in, then what you can see is the original data in blue and the model. Whether or not you compute it with C1 and C2 or with initial velocity, it doesn't matter. It's the same mathematics. They all go right through together. So these are ways you can use curve fitting to figure out parameters from experiments. Okay, so several ideas in here all the way through. Encourage you to go through and look at it again. Our lab next week will involve looking at some real data and doing some curve fitting and calculating accelerations and velocities. So we'll revisit this again on Tuesday and Thursday. That concludes the end of this particular lecture. Because I think it's right on time. Yeah, 3:15. We'll have the lab for those of you who have not yet done it. Again, I encourage you at least take a look at the current assignment, assignment 4, sooner than later. Try and do it in this lab section. Discuss it with me while I'm here. It should not be long, but I'd like you to try and get it done by Sunday evening so we can move on to the next bit. Are there any questions about data analysis, curve fitting, Taylor series, integrations, or anything like that we should discuss as a class? And you're welcome to come talk to me one-on-one on the screen in the back if you'd like. Otherwise, have a great lab, and we'll see you next week.